looking at number 5, be sure you balance this chemical equation. Here we're combining stoichiometry and some gas laws. In fact, well, here it says if 42.7 grams of ammonium nitrate decomposes completely into dinitrogen monoxide and water, what is the volume of steam? So I'm not looking for grams of steam, I'm looking for volume. But to get to volume, I'm going to start with my known here, and I'm going to do a little stoichiometry. And once I do stoichiometry, I can get moles of water, and I can take moles of water and put it into PV equals nRT to get the volume of the steam. Does that make sense? So let's do that. 42.7 grams of ammonium nitrate. And I'm going to divide that by the molar mass of ammonium nitrate so that the grams of ammonium nitrate cancel. Then I'm going to use the stoichiometry and cancel these. 1 mole of ammonium nitrate, that's what's up here in the balanced chemical equation, right here in front of ammonium nitrate, and 2 moles of water, that's what's right up here in the equation for water. That leaves me with this unit of moles of water. Hey, that's just what I wanted my unit to be in. I'm going to now take this and put it into PV equals nRT. There it is, right there. And I already had, of course, my temperature was standard temperature. That's what STP stands for. Remember, is standard temperature and standard pressure. So check your answer and make sure you got 23.9 liters of water. Number 6. Now, be sure you notice here that number 6 says to describe in a sentence. And rather than making a big, long description, we simply looked at this idea that if you take this chemical and mix them together, even though you know their original volumes, you can't predict their final volume. So we simply said, when we get our mass, we're just going to add that to enough water to bring us up to our final volume that was described in the problem. So in this problem, it says how do I prepare 400 milliliters of this 0.256 molar solution of sodium carbonate? Now I have to be sure and get the formula for sodium carbonate correct, or I'll miss the problem. Sodium is +1, carbonate is -2, so the formula is Na2CO3. If we take the concentration of our chemical and we multiply it by the volume, where the volume has been changed into liters, the reason we're changing the volume into liters is so this liters, which is downstairs, and this liter, which is upstairs, will cancel out, leaving us with moles, our unit right here. Now, we're going to take that moles and change moles of sodium carbonate to grams of sodium carbonate. That's our next step, and we're going to do that just by the tried and true method that you've learned all year long. Moles times molar mass equals grams of the sodium carbonate. So this is the mass we need to make, the mass we need to measure out, and then we'll add that 10.85 grams of sodium carbonate to enough water to make our 400 milliliters of solution. Number 7. Once again, describe in a sentence how to prepare 100 grams of a 40% solution. Don't make this problem harder than it is. These problems are quite easy. We're simply finding what is 40% of our total mass. That's how much solute we need to add. In this case, we're doing 40% is 40 grams per 100, where the 100 is our total mass, and that gives us 40 grams of our solvent. 40 grams is 40% of 100. So we're just going to add 40 grams of lithium bromide to enough water to make 100 grams of solution. Number 8 is about solubility rules and how to apply what you learned about solubility rules and double replacement reactions to write nat-ionic equations. So if you look here, nickel 2 chloride, that's nickel 2 chloride right there, and silver 1 nitrate, these are an aqueous solution. So they're floating around dissociated. Now, as the silver happens to come in contact with any chloride, they are going to stick together because silver chloride is not soluble in water. Now the nickel and nitrate, they're not actually going to form or precipitate. They're going to be dissolved in water, an aqueous solution. So what's the net ionic equation? The net ionic equation simply shows the stuff that's actually reacting, the silver and the chloride making silver chloride. That's the net ionic equation. And for the next problem, once again, we're looking for the cation and anion that are going to form a precipitate. The lead from the lead nitrate and the carbonate from the ammonium carbonate are going to make lead carbonate that is solid. That's the only thing we're going to show in our net ionic equation. Now, a couple of things to point out to you or remind you about in the net ionic equation. The charges of the ions are shown here on the reactant side, not on the product side. Of course, we have to use those charges to write the product correctly, but we don't show that charge when we write the product. Number 9 is back to some gas laws, and this is a special kind of gas law that we introduced called changing conditions. And we do this all the time, whether we're baking or scuba diving or driving and our tire pressure changes because the temperature changes. We make gases change conditions all the time. And in this case, the scuba diver is laying on their back in the water, deep, and they're blowing bubble rings. That's really cool if you've never seen it. Google it sometime, or Google some of the marine mammals that blow bubble rings in the water and then play with those. Hey, it's really cool. So they're watching those slowly rise to the surface. Now, the volume to start with is 0.5 liters, and that's just a little puff of air. The pressure is 3 atmospheres, so they're down around 60 feet in the water. Nice crystal clear water, probably not anywhere close to Oak Harbor. And the temperature of that water, 22 degrees Celsius. So those are the initial conditions, the pressure, the volume, and the temperature that we've converted to Kelvin. The final conditions are up at the surface. Now at the surface, the air pressure is 1 atmosphere, and the temperature is a little warmer, 311 Kelvin. So the question is, what volume do we have when this bubble reaches the surface? Notice the amount of air in the bubble, the number of molecules hasn't changed, so we're going to just not do any calculations and would factor out, and we've experimented with that in the past, so we're going to just kind of ignore n because it's not necessary for us to use it. Rearranging, so doing a couple of things here, correcting my formula. I had T1 and something else here. This needs to be T2 on the right of this equation. Rearranging that to solve for V2, we get this. And then substituting, we have V2 equals, and we're going to check our units and make sure that the units that cancel out leave us with liters. And then we're going to solve this problem and calculating that and getting 1.52 liters as the new volume of our bubble. Now moving on to the last few problems here. Number 10 and 11 are about predicting or just writing chemical reactions. You have word equations. All you have to do is write the correct equation here, And we're going to glance at these a little bit. Copper and sulfuric acid. Now, sulfuric acid, you'll find that on your common ion sheet. There are acids on the back of that sheet. And it says it makes copper sulfate. You just have to remember this copper 2. The 2 tells us the charge of the copper. Sulfate is -2, and those have to add up to 0. Of course, you know water and sulfur dioxide is made of 2 nonmetals. And anytime you see these prefixes, you know you have 2 nonmetals, and those prefixes tell you how many atoms of each element are present in the species that you're writing. As we move on to number 11, things like hydrogen, and there are a bunch of these elements that you know, and they're on your common ion sheet, that you write as diatomic elements, things like hydrogen and nitrogen. Of course, be sure to balance these by mass by looking to see here we have 4 hydrogen, and here we have 4 hydrogen. Here we have 2 nitrogen, and over here we have 2 nitrogen. Here we have 2 oxygens. This coefficient here in front multiplies through 2 oxygens there and 2 oxygens there. And number 12 is single replacement. You'll see that this bromine, a halogen, replaces the fluorine. So that's single replacement. And then the equation here, of course, is balanced by mass with a coefficient of 2 to give us 4 bromine on each side, and a coefficient of 2 for the fluorine to give us 4 fluorine on each side, and the carbon is balanced. Now this is double replacement because the hydrogen and the copper, the cations, simply trade places, double replacement. And this is balanced with a 2 in front of the hydrogen cyanide. Anytime you see a hydrocarbon combine with oxygen and produce carbon dioxide and water, that's going to be a combustion reaction. And here we have decomposition. Hydrogen peroxide decomposing into, oh, that's not correct. I'm going to have to fix that. Water and oxygen. Not sure how that got typed incorrectly. Okay. There you go. If you can do that, you can do the semester test.